Hi, Professor Rico.
Oh, hi. How you doing, Weina?
I'm good. How are you?
Okay, that's good. I'm trying to get situated. The problem with Zoom is everything gets in the way when I try to enlarge stuff. Sorry, there we go. So how was your semester going?
Yes, it's a busy semester. How about yours?
Yeah, pretty busy.
Sure.
I'm teaching two classes this semester, so I have to uh teach twice as long, but it's preparing notes and homework, all that stuff. So teaching one undergraduate, actually it's two graduate courses, but the one course I teach is also a lot of seniors, and they're
Um,
getting ready to graduate, so I don't think they take it too serious, because they just want to graduate, worry about anything else. Anyway, so how are things at Stevens?
just teach one class, but I submitted several proposals on the Young Investigator Awards for DOE, DOD, and different agencies. So it's a little
Yeah.
busy
Yeah,
on
that
that.
you just have to. Yeah, I can imagine. You got to stay one step ahead of the cycle with students because you got to think of next year
Yeah.
already because it takes time for these proposals to get reviewed.
Yeah. Yeah.
So I've had a couple of my prepared, but then I had to prepare at least another two this semester. So it never ends.
Never
Okay,
ends.
I'm
Yeah.
gonna open it up so people can start coming in, and then I'll do an introduction in a few minutes.
Thank you,
Okay.
Tom.
So Tommy, I have Dr. Mien. I'm gonna pronounce it right. Mien it's Mien.
Meng. In Chinese is Meng.
Mung,
Meng.
Moi?
Or
Mung.
Meng. Or Meng.
Hey,
Meng is,
okay, sorry. Well, Dr. Weina May, right?
yeah.
Okay, sorry about that. I'm better at spelling it than pronunciation. Anyways, Tommy, I have the background here. I could introduce our speaker and give a little bit of a history of why we do these
Yeah, we'll get there. Just give it a few minutes.
this forums there. So Ali has been designing the working now with Liang Cao, the footprint. We're thinking you can develop with your high performance concrete. You could put it underneath the CLT rocking wall there. In order to harden, I guess the what you say, the toe or the heel of the wall, that it avoids failure there. So she's worked out some preliminary stuff, but I think Liang would take over that since Ali is going to be working on another project as well. But Liang's actually been overseeing a lot of the testing on the CLT wall. But so we should be getting back to you pretty soon there,
Okay.
Rena.
Okay.
That would be
Uh,
great. I'm
yeah,
looking
I know
forward.
you're anxious there. So we're thinking, we can give the design if you want to cast a unit where you are, or you can cast it here, whatever is easiest, but there's like a fit. So the wall is here and you cast a unit, you kind of, it's like a shoe. We're gonna put it over the end of the wall and then bolt it in place. So we'll have to figure out a little bit of the details, but I think when we get far enough along, which we almost are there, we can have another Zoom to work out some details. It's more working out than the logistics.
Okay.
Okay,
Right.
Jim, we're gonna get started. All right, all right, so it looks like everybody's in. First of all, I want to welcome everyone to the continuing NHERI Lehigh seminar series today. For technical details, if anyone has any issues, you can type in the chat and I'll try to help you resolve any of those issues. But as far as questions and comments, just please put them in the chat or Q&A. We will hold all questions and conversation until the end of the webinar. And then with that, Dr. Rickles, if you'd like to introduce our speaker, and Dr. Meng, I will allow you to share your screen.
Oh, okay. Well, first, my name's Jim Reckles. I'm the excuse me, the director of the facility, working with our staff, our colleagues. Tommy Marilla is one of them. Ali Amir is our NHERI postdoctoral uh, fellow, and so we have a number of staff. And let me just give you just a brief background before I introduce the speaker about our purpose, our seminar series. So we hold these about almost about once a month, and the purpose is to provide a forum for the presenter to disseminate findings from their research. Could be very recent or ongoing research. So it's either concluded or it's ongoing. And it's to basically enable the community to become aware of the work that they've done, and also how Lehigh can try to help that work further along. And it also helps to connect with the funding agencies. Now we have various resources available at our facility, and so a lot of this work is in conjunction with some of these facilities. And so I want to encourage you to visit our website, NHERI, NHERI, Lehigh. If you Google that, you'll eventually get to the right web page. And our facility expertise, while it's in real-time hybrid simulation, we like to say we try to be a little bit more general, that we do multi-directional simulation, of which Dr. Mien is going to be participating in some very important work. So with that, let me go ahead and then now introduce the speaker. As you see, the title here is Innovations in Ultra High Performance Concrete, UHPC. Going to focus on sustainable practices in AI, which is artificial intelligence assisted design strategy. So Dr. Mien is a tenure track assistant professor, but a very hardworking one, because every time we try to interact with her, she's very gracious to do this. But I know she's very busy, but we're very fortunate to have her here today, and that her work specializes in sustainable and resilient civil energy materials, something very important, for infrastructure. Now, her work focuses in really 4 general areas. So first is advancements in ultra high performance concrete, as you can probably gather. Another one, she's been doing some pioneering work in CO2 sequestration in concrete, developing biomimetic concrete, and utilizing artificial intelligence for enhancing concrete design and analysis. Dr. Mien's received recognition, various awards, including the NSF Career Award, and being named among the world's top 2% scientists by Stanford University. She's very active in publishing her results. It includes, to date, 66 peer-reviewed journal articles, has a U.S. patent, edited 2 books, and over 4,000 citations in Google Scholar. Also, she's gives a lot of focus on education, so she's been named the 2020 Educator of the Year by the ASCE New Jersey section. Is quite an honor. And lastly, she's very active in the community, especially in service, and that she holds memberships on the ACI, ACS, and ACER-S, as well as she's holds editorial positions on 2 journals and contributes to the standards developed by the American Concrete Institute. So with that, I'd like to then give the podium to Dr. Mien, and we look forward to your presentation.
Thank you very much, Professor Rickles, for the very nice introduction. So it is really my great honor to be here to present some of our current work on the ultra high performance concrete, or UHPC in short. So today I will cover 3 main contents. One is the problems and the novel solutions of UHPC for the application of the bridge deck overlay. And then I will discuss how to further improve the UHPC materials on the perspective of sustainability. And then finally, I will introduce how to use the artificial intelligence methods to design and optimize the UHPC for sustainability. So currently in the US, there's a high demand of bridge maintenance due to the spalling, delamination, and rebar corrosion of the bridges. And many of the bridge decks needs to be repaired. So the most popular repairing materials for the bridge deck overlay include latex, modified concrete, the LMC, the low slump dense concrete, the LSDC, the high performance concrete at HPC, and the UHPC, ultra high performance concrete. So compared with other types of repairing materials, the UHPC enables much thinner thicknesses for the overlay construction, and also it exhibits much higher mechanical properties. And more importantly, the UHPC has much better durability, which could allow extended service life, as you can see here. So UHPC is considered as a very promising repairing materials for the bridge deck overlays. However, there's several critical challenges of the UHPC to be used as an overlay. First is it has a high cracking potentials, mainly because we use the high binder content in UHPC, and that results in high shrinkage at early age. So the high shrinkage will introduce high tensile stress when it exceeds the tensile strength of the concrete, especially at early ages. It will crack the bridge deck overlay. So the second big issue is the difficulties in slope casting. So for the majority of the bridge deck, it is a sloped structures with a slope somewhere in between 2% to 5%. But the typical UHPC, as you can see, is very flowable. So it could flow from the top to the bottom, and it is hard to stay on the deck. So intensive labors and formworks usually will be needed for this kind of construction. So the third problem we have here is the difficulties of in large-scale production of UHPC. So as you can see, usually during the mixing, the mixer will be shut down if you mix a large volume of UHPC. But it's really not the case for using the normal mixer to mix conventional concrete. The reason is that, as you can see here in this figure, so here shows the mixing torque evolutions for conventional concrete. The peak mixing torque is really very low. It's much lower than the capacity of the mixer. So that's why for mixing conventional concrete, there's really not a problem. But for UHPC, if you mix the same volumes as the conventional concrete, the peak mixing torque will easily surpass the capacity of the mixer, and that caused the stoppage of the mixer, and that may damage the engine of the mixer and waste all the raw materials. So those are the three critical challenges we identified. So to address the first issue, the high cracking potential, the most effective way is to reduce the shrinkage of UHPC. So properly use the internal curing agents or shrinkage reducing admixtures or the expensive agents. This shows a comparable shrinkage mitigation rate as summarized in this table. However, using the internal curing agents, usually we will need at least 24 to 48 hours to pre-saturate these types of materials, and that is identified not very practical. And for the shrinkage reducing admixtures, even though it is very effective in reducing shrinkage, but it is reported to have adverse effect on the mechanical properties, or reduce the mechanical properties. So compared with the other two methods, using of expensive agents is easy to use kind of method, can reduce the shrinkage a lot without mitigating the mechanical performance. So in our study, we try to further improve the efficiency of the expensive agents to improve the expansion effect for reducing more shrinkage. So we simply add the dry expensive agents into water for a couple of minutes to allow enough sufficient water and space to for it to grow more expensive products, and so that to enhance the expansion effect. So we use the ring test for the evaluation, and we installed the distributed fiber optic sensors on the ring specimens. So this will allow us to measure the shrinkage stress development, and at the same time, we also measure the tensile strength development of the concrete materials. and using those two results to calculate the cracking potentials with time. So usually if we can have the tensile strength development always surpass the shrinkage stress, then we will have the concrete with very good cracking resistance. So here we compare like 3 groups of UHPC mixtures with different shrinkage reducing strategies. But for each of the strategies, we all use the expensive agent. And we compare the case with and without the pre-wetting method. So the result shows that with the pre-wetting, we can significantly reduce the peak cracking potentials as well as the cumulative cracking potentials. So that's for the best mixtures with a 4% expensive agent, 50% internal curing agents, the lightweight sand, and some 45 minutes of pre-wetting. We have the mixtures until now didn't see any cracks. So for the second problems related to the slope casting, the effective method is to enhance the thixotropic properties of UHPC, because the thixotropy can enhance the shape stability of the UHPC after casting. So as you can see, with high thixotropy, the UHPC can stay on the sloped panels. So we can, which can help us to minimize the formwork and other like construction related costs. So the typical way to enhancing the thixotropy is to use nano clay powders. However, this method, as reported, it has very severe agglomerations of those types of nanoparticles. So these agglomerations will have very adverse effect on the mechanical properties as well as the durability of the materials. So to avoid such agglomerations, we use the very well dispersed, the water-based nanoclay suspensions to enhancing the thixotropy. As you can see, the thixotropic properties can be very effectively enhanced. So with the enhanced shape stability, the fresh UHPC can stay on the slope without external supports. And we also evaluate the interfacial properties of the UHPC and the substrates concrete. So we're using the direct shear test to evaluate the bond strength in between this interface. And also we quantify the interface voids, the voids at the interface by the microstructural analysis. So the result shows that the increase of the thixotropy by increasing the nanoclay content would reduce the bond strength. This is because the more air voids were introduced at the interface. So it is suggested that a little bit vibration should be applied to the thixotropic UHPC in order to reduce the air voids and improve the bond strength. But for the vibration, we could optimize this process. We can use the minimum vibration time in order to achieve the acceptable bond strength, as there's a development of the bond strength with the increase of vibration time, and it was stabilized after a while for different mixtures. So for the third problems, to address that, in order to facilitate the large-scale production of UHPC, we should first of all understand the mixing torque evolution during the mixing process. So the most difficult time is when the materials transform from solid to liquids. And after that, the torque will reduce to very, very small, and it represents the homogeneous time. So, and also by understanding the key impact factors on the mixing kinetics, we could optimize the mixing procedures for the UHPC production in large scale. So in our studies, we investigated 3 key parameters: the mixing temperatures, the mixing volumes, and the mixing methods. So specifically for the mixing methods, we have a mono batching method. It means we add all the raw materials at the same time and then add the water and the chemical admixtures and homogenize it at once. And for the multi-batching methods, it means that we equally divided the raw materials into 2 to 3 portions, and we add one portion and homogenize it, and then add the other until we add all the materials and homogenize them. So from our results, we find that both the temperature and the volumes, so increase of the volume and temperature significantly increase the mixing torque. And the peak mixing torque is more sensitive to volume than the temperature, as we can see in this analysis results. And to do the multi-batching can be effectively reduce the peak mixing torque. And look at the curves of the mixing evolution curves. We saw that it's quite similar with the Gaussian distribution curves. So based on that, we proposed a mixing kinetics models to describe these curves. So as shown here, where the A, B, C, alpha, beta are constants, which can be determined by regression analysis. And the T here represents the mixing temperature, and the V is the mixing volume. And T here is the mixing time. So again, by the regression, we can determine the constants for the model and use the model to predict the mixing kinetics curves. So we developed this model is because we want to use that to optimize the mixing process for any large volume of UHPC. So here shows the case study. So if you have a certain UHPC mixture design, so when you have that, the first thing you should do is to determine the model constants by conducting some small batches of UHPC. And once you determine the constants and given the volumes that you target to mixing and the mixing temperatures for constructions, and you can determine the mixing torque for mono batching, 2 batching, or 3 batches. And after that, you will need to, given the mixer you have, you may have a normal mixer, pan mixer, or high shear mixer, whatever the mixer you have, you can calculate the mixing capacity of the mixer. And once you know that, you can see, you can just compare the different like mixing torque evolution curves with the mixing capacity. So in our case, if you do one mono batch, it's definitely your mixing will not work. So what you can do is a 2 batch will be sufficiently enough for a successful large volume production if you use a normal mixer. So this is the 3 batching method. As you can see, it's very, very smoothly mixed. So we address this problem. So in a brief summary, our contribution to the UHPC overlay is we addressed the critical issues. We developed the UHPC with low cracking potential, and also we developed the methods to for enhancing the shape stability of UHPC for sloped casting, and also we developed the fundamentals for the optimization of the mixing process for large-scale production of UHPC. Now, from the previous slides, we learned that the UHPC can be tailored with exceptional performance depending on the applications. And but still, for the production of UHPC, for the commercially available UHPC, as you can see, the initial materials cost is still very high. And also, the CO2 emissions is 6 to 8 times of the conventional concrete. So currently, we proposed many strategies to decarbonize the UHPC. So it includes integrating the low carbon ingredients, advancing the processing methods, and developing the new construction techniques. So in the interest of time today, I will focus on the utilization of solid wastes and our work on the intelligent design for sustainable UHPC. So for now, the major work on developing sustainable UHPC materials is to replace the cement with high volume of supplementary cementitious materials such as slag and fly ash. However, those typical supplementary cementitious materials are really in high demand. And also it's reported that the supplies of some SCMs are diminishing. And there's really a need to find some alternatives. So in this work, in our work, we try to find the alternatives, specifically the high carbon and porous types of wastes to replace cement to develop the low carbon and cost-effective UHPC. So the high carbon waste materials I will introduce here today is the off-specification fly ash, OSFA, and the biochar. So we consider those two materials is due to its high potential and the large availability. So again, the off-specification fly ash, as you can see, it has like very large amount. Just 2 and 3 years ago, it's still very a large amount, and it is really target for landfill. And different from the normal fly ash, the OSFA, it has very low reactivity because as you can see here, compared with the normal fly ash, it has negligible reactive kind of oxides in the system. So the majority content is carbon. And so that will reduce the mechanical properties as well as the durability of concrete. And also the OSFA has very low density. And due to the high surface area of the OSFA, it absorbs some chemical admixtures and some ions. Specifically, it's reported that it absorbed the air entraining admixtures, which could reduce the freeze and thaw durability. So there's a lot of problems for the OSFA. So in our studies, we investigated 3 groups of UHPC with different binder system. So the first one is a control. So we have 100% cement. And the second one is a binary system. We have the OSFA with different content and the cement. And the third group is the 2% fixed OSFA, 20%, sorry, OSFA with different content of slag and cement. So as expected, if we use the OSFA to replace cement, what happened is both the compressive strength and the flexural properties significantly reduced. So the reason is that the OSFA retard and hinder the cement hydration due to 2 effects. First is the dilution effects. So OSFA is inert. It is much less active than the cement. so it has much less cement hydration happen there. And the second is the adsorption effect. So as the OSFA has very high surface area and high carbon, so it absorbs the calcium ions dissolved from the cement. So that will hinder the precipitation of hydration products. But the good thing is that if we incorporate the slag into the system, especially if we incorporate 40% of slag in the binder system, we can increase the 28-day compressive strength by 50% and increase the 28-day flexural strength and toughness by 20 and 10% respectively. So the enhancing mechanism is that, first of all, the slag has different size than the OSFA and the cement, so it can enhancing the particle packing densities of the microstructure of the system, which can enhance or refine the microstructures. And also due to the improved particle packing densities, we can release like more free water and reduce the use of high range water reducer. So it's basically a long chain polymers. So we can expose more cement to the water and for the cement hydration. And also by using the slag, as the slag is a pozzolanic materials, it will promote the pozzolanic reaction and form like more dense and strong hydration products. And also both the OSFA and the slag shows the benefits in reducing autogenous shrinkage. Basically, both of them could release or increase the free water in the system and increase the free water in the capillary pores so that we can mitigate the self-desiccation induced shrinkage significantly. So in terms of the sustainability, as we use two types of waste materials in the system, we could reduce the strength normalized materials cost by 20% and reduce the strength normalized CO2 emission by 50%. So as you can see here, the maximum OSFA we can use in this specific study is 20% without mitigating the strengths. So to further improve the utilization rate of such waste materials, we're thinking to strengthen these porous structures with the nano calcium carbonate. So to create this calcium carbonate, we use a CO2 sequestration technology that we directly inject the CO2 into the calcium hydroxide rich solution. And this solution was prepared with the OSFA, so we can coat the surface of the OSFA with the nano calcium carbonate. So with that, we could significantly increase the utilization rate. So the second high carbon types of waste were considered is the biochar. So the biochar is produced through the pyrolysis process by the biomass. So it has very similar features as the OSFA, has very, very low density, very high carbon carbon content, and very high surface areas. And because of the high carbon and high surface area, it is usually used as the soil treatment materials or to remove the heavy metals from the wastewater. So we look into the microstructure of the biochar and found it's highly porous. So we're thinking to utilize these types of wastes as internal curing agents. So what we did is we pre-saturate the biochar in water for 24 hours to make it saturated surface dry. And with this water, so it works as a reservoir and absorbs some water inside. And when we put into the cementitious systems, it will hold the water during the mixing and release the water during the hardening process. So compared with external curing strategy, especially for a very dense types of concrete, it can provide much effective curing for the concrete. So we investigate two cases of biochar. The first is a fresh biochar, and the second is we use the fresh biochar and immerse them into the heavy metal solutions for 4 hours. And we call this types of biochar as a used biochar. And for both of the biochar, we pre-saturated them for 24 hours before use. So both the biochars improved workability. And the reason is that the biochar has like smaller sizes compared to the cement and slag, and they improve the particle packing density and release more free water for lubricating the particles. And also here, one thing I want to note is that for most of the studies that they utilize the biochar in concrete, they saw significant drop in mechanical strengths if you directly using the biochar. But in our case, as we use this as an internal curing agents, with 1% the optimum dosage of the biochar, we compare with the control, we have the 28-day compressive strength, flexural strength, and toughness increased by 10%, 20%, and 25% respectively. And again, not surprisingly, as we use the biochar as the internal curing agents, as we can more effectively cure the UHPC, so we can have the autogenous shrinkage significantly reduced. So even though for the biochar we didn't use a large amount, just very small, 2%, we can have a very, very high reduction in the CO2 emission, as the biochar itself is a carbon negative types of materials. And also from the leaching test, we observed that the UHPC can lock the heavy metals permanently inside of it, especially for the used biochar cases. So this also demonstrates the environmental benefits of this study. So in a brief summary, the utilization of the waste materials in UHPC for the sustainability should be treated case by case. So different strategies should be applied for different waste materials. For OSFA, we should use the slag to further improve the reactivity of the system and improve other properties. And for the biochar, as it has very high amount of pores, so we could utilize it as internal curing agents to improving the overall performance of UHPC. So besides the biochar and OSFA, there are actually hundreds of different types of waste materials are considered to develop the sustainable UHPC. So here there's really two major ways to design or optimize the UHPC. The first is particle packing model-based methods. So this is the model people usually used for high packing density. So, but this methods, it can help the system to achieve very high particle packing densities, but it does not guarantee the key properties are high performance, such as the tensile properties or the shrinkage or the durability. So because of that, the majority of the research, they use the performance-based methods. So for these methods, people want to achieve the target performance. So they have to do like step-by-step testing, optimize the binder system, and then the concrete system, water system, and then the concrete system, or fiber reinforced the concrete system. So as you can see, this method is involved extensive experimental testing, and it's costly, time-consuming, and labor-intensive. So there's really a need for a more efficient and effective methods to design the UHPC. And because of that, currently we developed the AI-assisted design framework for auto discovery of low carbon cost-effective UHPC. So for this framework, first of all, we should collect large enough data or the source of knowledge and forward the data to develop the machine learning model for prediction. So in this case, the input is a concrete design variables and the output is a concrete properties. And once we get a very accurate prediction model, and we will embed the optimization and decision-making algorithms for the intelligence optimization. So in this case, the input is the target properties and the output is the optimal design. So the data we need are two sets. One is concrete design variables, include the types of the ingredients, the mixture of variables, the processing schemes, and also we will need the second set is a UHPC properties, the fresh properties and hardened properties, like the mini slump flow, the flow time, the flexural properties, Young's modulus, shrinkage, and so on and so forth. So in our study, for our research, we tried to collect large amount of useful data more efficiently, and we developed the AI data collector, data generator, and data processor, and to automatically determine the most appropriate machine learning model, as there's many, many machine learning models. So we also developed the AI auto learner, and also to optimize the UHPC, by considering many objectives, as our target is to design a sustainable UHPC, low cost, and also we consider high mechanical strength and durability. So it's a multi-objective kind of optimization. So for that, we developed the AI optimizer. And last, not the least, to consider the variations in chemical and physical properties of different wastes, we developed the AI data presenter. So for the AI data collector, we developed it to automatically collect the available data from the published documents. So we collect the data from journal papers, conference proceedings, the reports, et cetera, So this collected data can be automatically updated through tracing and extracting data from the new publication. So we can always get the newest data and largest amount of data for the machine learning models. So by using the AI collector, if we collect 1,000 data, we just need 1 hour. And before that, we tried collect 1,000 data, we will need manually collection will need around 1 month. So we'll significantly reduce the time with high efficiency and high accuracy. And also the AI data collector has a function of self-updatability. So it will improve the accuracy by increasing the data sizes. And it enable the consideration of new materials because there's more and new solid waste are considered in the new publications. So we can involve all those data in our machine learning models. So also the self-updatability will enhance the accuracy of the machine learning model with time and reduce the life cycle cost and carbon footprint with time, because we consider, as mentioned, we consider like more and more new types of waste materials for sustainable UHPC. So, for some of the case, we can collect sufficiently large data, but for some of the case, especially if we consider some new materials, the published results may not sufficient. So in that case, we will need to generate the data or generate artificial data to enrich our data set for a high accuracy of models. So in this case, we proposed the 2 methods to generate the artificial data. One is to use established theories or equations. So here is a relationship well established for tensile strain and the steel fibers, the fibers characteristics. So given the different values of the fibers information, we can get a series of strain. So this is one type of way to establish like new data. So the other is to use the advanced machine learning techniques such as the generative adversarial networks, the GANs. So the idea or the concept is the same as we transform an image to the style of Van Gogh's Starry Night pens. So the GANs model learn from the existing real data and generate the artificial but reasonable and useful artificial data or AI data. And we combine the AI data with the real data as a synthetic data so that we use the enriched data set for machine learning model training. And now we know how to get the high quantity of the data. Now the next question is how can we get the high quality of the data? So to that purpose, we will have to identify and properly remove the anomalous data from our data set. So the good thing is that the anomalous data usually have very different features from the normal data. And through using the supervised and unsupervised learning, we can rank the data by their anomalous. However, the ranking of the anomalous data is based on the data-driven methods, not based on material science. So it could treat some of the normal data as anomalous data. For that, we proposed a contamination ratio, which is defined as the percentage of anomalous data in a data set. So we found, so through parametric studies, we found that it's not like we remove all the anomalous data, we get the highest accuracy, but there's an optimal contamination ratios will gives us the highest accuracy or the minimum error. And also the variables we selected should be optimized in order to have a higher accuracy of the machine, to achieve the higher accuracy of the machine learning models. The reason is that if we consider like extra variables, the machine learning model will be very complicated and inaccurate. And if we exclude the necessary variables, it's also not good because the machine learning model will be inaccurate too. So the criteria for the variable selection is that, first of all, we should have the variables independent to each other. For example, we cannot include the water content and the water to semen ratio at the same time, right? So because they are dependent. And also the design variables are highly correlated to the concrete, should be highly correlated to the concrete properties. So here shows one of our studies, and we found that it's not like we consider all the variables we get highest accuracy. It is when we considered the most independent and highly correlated types of variables with 21, we get the highest accuracy. So variables is selective as well. So in terms of the machine learning model determination and selection, for now, there are many machine learning models, include the individual models and ensemble models. So overall, the ensemble models performs better than the individual models, but the different models have different performance. It's really depending on the specific problems and the features of data you adopted. So in our work, we automate actually the development of high fidelity machine learning models. So different from the current practice, our work involved the automation of model selection and combination. So different types of models are combined to achieve high accuracy. And also the hyperparameters is automatically optimized, so as the model complexity is automatically minimized. So our methods, as you can see the Taylor diagrams, it achieve the highest accuracy as our result is most closest to the observed. And now we get like high accuracy of the machine learning prediction models, and then we can move to the intelligent optimization. So the optimization of the sustainable cost-effective UHPC is actually a multi-objective optimization. So we should simultaneously optimize the environmental, economical, mechanical, and durability properties at the same time. So the method here is that we should first of all collect the data we need, mainly the concrete design variables and the concrete properties, and use those data to develop the high accuracy machine learning models, prediction models. And at the same time, we collect the inventory data and use the data to calculate the environmental and economical properties, such as a carbon footprint, environmental energy consumption, and the costs based on the raw materials. And once we have this collected, we will define the constraints and objectives and embed the optimization algorithms and decision-making algorithms in order to output optimal design. So the evolutionary optimization algorithms are used to search for the optimal solutions through minimizing the objective function defined based on the design objective. So here shows the example of how we use the AI design method to design a grain UHPC. So here we considered many types of different waste materials. So the design constraints we set is the mini slump flow should no less than 260 millimeter. And we set the 28-day compressive strength no less than 120 megapascal. And for the design objectives, we should minimize the unit cost for cost effective, and minimize the unit carbon footprint and maximize the compressive strength. So our results, as you can see, we reduce the cost by 65% and reduce the carbon footprint by 56%. However, the existing models also show some limitations, especially when we considered various waste materials, because the waste materials is usually considered or designated with their engineering name. We just have it as a fly ash or slag or the waste glass, whatever. But those waste materials, they actually have very different physical and chemical properties. As you can see, for fly ash, different type of fly ash, they have very different chemical compositions, as well as the physical particle size distributions. So those are not considered in the AI models. So currently, we develop the methods and create artificial language to describe this waste materials in chemical and physical properties. So what we did is that we first of all define some symbols to describe like different chemical variables or physical variables, and then we assemble those symbols into sentences and assemble the sentences into essays. So it's through this artificial language and the text mining, we transform the essay into numerical data and use the data. We perform the deep learning and to predict the concrete properties. And most importantly, we can use these methods to unlock or investigate some unknown chemical reactions, because we can evaluate in the interactions between the pairs of different chemical variables. So the example shown here, as you can see, here shows the interactions of the different oxides in cement. So we can clearly see which pair of oxides shows most significant interactions. This means the strong chemical reactions happen there. So in summary, for this work, we can use the AI-based design methods or the prediction optimization framework to design the sustainable UHPC. And also it is possible to use the AI method to investigate the unknown chemical or physical reactions of the new concrete system. So for the interest of time, I didn't elaborate some of the information, but all the things I presented today were published. So some of the publications are shown here. And here are some publications related to the UHPC materials development. And also, I want to take this opportunity to thank all the important contributors. So Mr. Peng Wei Guo, so he's one of my PhD students who will graduate this year, the end of this year. So he's a very excellent student. And also Dr. Jiang Du, he was graduated last spring. And Dr. Surush Majobi, so he's now a postdoc in MIT. He was a PhD student of my colleague, Professor Ibao. And also I would like to thank my colleague, Professor Ibao, for his great contribution. And also thank for all our sponsors to support our research. With that, I would like to thank all of you for your attention and would like to take any questions if you have. Thank you.
Great. All right. Thank you, Meng. Dr. Meng. So we have one question in the Q&A right now. You want to, it's up to you if you want to read it or you would like me to read it out loud. It's up to you.
Okay, just let me read it.
Okay.
So there's questions so was the ductility of members studied for reinforced UHPC members? And is it considered to be superior for earthquake resistant design as well? So actually my main focus or my expertise is on materials, but we also collaborate with Professor Bao. He's a structural engineer. So we developed some types of new UHPC considering the waste material. So we developed the beam structures and we conducted the ductility tests for some members. So yes, so I think from the best of my knowledge, there's a lot of studies using the UHPC for earthquake kind of structures. I think it exhibited superior performance for the earthquake application.
Okay, thank you. And then there's a question, a raised hand. I'm going to open that up.
Okay.
Okay. All right. Forgive me for not Jada. Jada, is that how you say Gahada? How you say your name? You can unmute. I'll give them a second. Okay. Well, while we wait for one of the questions from the chat, Dr. Rickles, if you're still there, if you'd like to jump in and give any final closing remarks while we're waiting to see if there are any more questions.
Yeah, so Weina, I think that, Dr. Mann, this is very interesting subject there, and I think with the infrastructure deteriorating, it seems like this would be a good use of some very advanced materials. Or how far are you into where you think it's almost to be implemented? In other words, you're studying some of these issues with the slope maintenance, the binding and the agents, but at this point, are you further improving it, or you have now come up with a mixture that you didn't need to put to the test by then testing on in structural applications?
So actually for the overlay work, we collaborated with the teams from Rutgers, and this work was supported by the New Jersey Department of Transportation. And I finished the phase for the materials development and assist with the specification development. And I think they are now in a process of implementing the materials for actual portion of a bridge.
Okay. That's interesting.
Thank you. So I received another questions from Dr. Zhang, and he asked, or she, does dividing the mixing of UHPC into multiple times affect its mechanical properties? That's a really good question. Actually, we published this work on construction building materials. So we actually investigated the effect of different batching methods on the mechanical properties, shrinkage, and the durability as well. So we didn't see a significant difference from different batching methods. So I think so it should be fine if you divide it into. Actually, we see a little bit improving in mechanical properties because even though you divided the mixing torque, also reduce the mixing torque, but extend the mixing time. So with higher mixing time, you have the particles like more like frictious, and it's like improve the hydration, and that gives you higher early age strengths. Thank you for the question. So for more details, you can look into our papers on that.
Okay.
Thank you.
All right. And Dr. Rickles, if you'd like to and make any final remarks, I don't know if you had anything else. Otherwise, we will end the webinar after give you a time to give any closing.
Yeah, so I think first, I think I'd like to thank the presenter. I think this was very informative, very important here. And so, with that, I'd like to thank you, and I look forward to seeing some more results, particularly on the where you can have this used to develop performance-based, I guess, renovation, or even for new structural systems where you take advantage of this material there. So, I want to thank you then again for presenting there, and wish you the best of luck and success in the future there of your work.
Thank you very much, and I really much thankful for the Lehigh team to inviting me for this very nice presentation and seminar, and I'm looking forward to work with you in the future for extending the application of UHPC. Thank you very much.
Yeah, you're very welcome there.
Okay, well, we appreciate everybody taking this time today to join us on the NHERI Lehigh Seminar Series. If anyone is interested, in about a week, this will be posted on the Design Safe website under the Lehigh section, and we will be continuing this series throughout the year. So look forward to more announcements from us. We thank everybody for your time.